Okay, well, it's Friday. One more little period, then we can take a break for a couple days, right? This is really gross, right? You'd think the folks would realize I should probably brush my teeth after drinking soda, but I hate even looking at those pictures. So there's bad ways to handle acids and bases. I mean, it doesn't even have to be a strong acid or base, and they can cause some damage over time. So hopefully we're not going to be talking about misusing these things. We're talking more about using them correctly, right? And the benefits are fantastic, right? Here's just obvious ones, like cleaners and that sort of things. But the point is acids and bases are everywhere, and we want to talk about them. And what's odd is that very rare, very few of them are strong. In fact, well, let's take a look at an animation here. Because we have strong acids, we have weak acids. So what does all this mean? See, maybe this little molecular animation will help. Okay, so first we're clicking on hydrochloric. You have hydrochloric acid and you have hydrofluoric acid. Hydrochloric is HCl, hydrofluoric is HF. So they're going to bubble HCl gas into here first. Right? Here's what an HCl molecule looks like, a chloride anion and a hydrogen ion. So they bubble it all in there. At the molecular level, they're trying to show you how the populations, it's all dissociating, right, into hydrogen ions and chloride anions. So that would be an example. HCl then would be an example of a strong acid or a weak acid. Strong, right? Because strong means there's going to be, it can do a lot of damage. It has a lot of hydrogen ions, right? Huge concentration. In fact, there isn't any HCl. HCl doesn't even exist. It 100% dissociates. Let's take a look at hydrofluoric acid. So bubble hydrofluoric acid into water. This is all into water. So you got a lot of hydrofluoric acid. And at the molecular level, here's an HF molecule, fluoride and hydrogen ion. Oh, there's one. Did you see it? There's a little guy floating around. All right, so it's rare. Here's a hydrogen ion and a fluoride anion. So this HF, hydrofluoric acid, is a weak acid. Okay, but is it an acid? Yeah, it's an acid. It's just a weak acid. Okay, so that affects its chemistry. So by looking at those videos, Bowdy, how would you answer this question? Strong acids are perfect, 100% dissociated in water. Okay. There are 6 strong acids. Okay. Now, Cameron, I'm going to give you a clue for half of them. If you remember this clue, you got half of these 6 strong acids knocked out for the quiz that's coming up on Monday. They are the halogens, which on the periodic table. These strong acids are H and a halogen. That's 3 of them. What are they going to be? And we've heard of them in lab. All right? What are the halogens?
Right
7.
yeah.
Right before the nobles. So put H with Cl. All right, there's Cl. Because remember, you've heard of this. H is in front, it's an acid. Well,
I got a question. Is it a base like, say HClO? Would that make it a base?
we're going to talk about that. We're going to talk about that, how to make bases and acids. But right now, we got to get through this this idea first. HCl, HBr. There's one more, HI. There's the 3. Just don't pick HF, okay? So there's three. We're halfway done. There's three more. Man, does anyone know any of these? Ooh, H2SO4. So how do we call these? Hydrochloric, hydrobromic, iodic acid. Okay, and then someone said H2SO4. Sulfuric acid. And then someone said HNO3. That one's called, that's the dangerous one actually. Nitric is the dangerous one, I think, because you don't feel it doing its damage on your skin for several minutes, and by that time it's spread all over your face. Nitric acid. Last one, perchloric acid. Okay, so definitely know all these six. Definitely know them. Know the names and formulas of those 6 strong acids. And there's going to be a reason why. We're going to see it pretty soon here. If an acid is not strong, Kendall, then we're supposed to call it weak, right? How can we easily recognize if an acid should be considered weak? First off, Kendall, let me ask you this. Just in the world, would you think there's more strong acids or weak acids? Weak, right? Because an acid is anything with an H out front. So there's going to be a lot of weak acids. How can you tell the difference? Anybody? How could you tell the difference? Well, that wouldn't make it hard. It might help, but it's not one of the 6. Exactly. That's why you know the 6. Because then anything else with an H out front, it's going to be weak. That's how I do it. So how do you know if an acid's weak? It's not one of the 6. Exactly. Not one of those. Strong acids. We can write HA goes to what plus what? What would you write, Jose? Just a general way of saying this. HA goes to, like this could be HCl. It's just A is just a general way of writing this. So it would go 100% to what plus what? H plus, right? And what would be left? The general way of writing this. A with a minus. Right, so that's just the general way of saying this. Here's a strong acid. I don't care what it is. It's going to go to H plus and then the anion. Okay. And notice how it doesn't go back the other way. What's the words for HA and A minus? They are, starts with the C. Conjugates, right? Look at that. This conjugate acid is super strong because it goes that way. This conjugate base must be super weak because he's not going to grab the H and go that way. So you can kind of think of why this acid's so strong. You can kind of think of it as, oh, it's strong because that acid's strong. Or you can think of it so strong because its base is so weak. 2 ways of thinking the same thing. We can write the exact same reaction, but we're not going to do it this way because it takes more writing. Is HA goes to H2O plus H2O, 100%, you get what plus what? Hydronium. That hydronium, exactly. Hydronium and what's left? A minus, right? That H grabs onto the H2O, and you get that hydronium. But you know, it seems like it's more work to write it this way, so we never do. We're always going to be writing this top one. Even though, remember, bare protons don't exist in water. They really exist as hydronium ions, but okay. So we're kind of getting into this, answering what Cameron was asking a little bit earlier, is how do you know what a base is and how can you recognize one? Well, here's a big table of all this stuff, right? It's got the acids on this side, and they're what base? Starts with C, Audrey? conjugate base. So these are conjugates of one another. And then they list them in order of the strongest acid to the weakest acid, or the weakest base down to the strongest base. So notice how the strongest acid has the weakest base. So that's the game that we're playing here. Let's see if we can answer a few questions. Which conjugate acid would you say, Jose, is the strongest? HClO4. Okay, so we're just going to play around and see if we can read this table. Which conjugate base is the weakest, Andromeda? Yep, with a minus. Perchlorate. Okay, Steph, how are we going to finish this sentence? The stronger the conjugate acid, then the blank the conjugate base. The weaker. See if you can answer this, Megan, by looking at the table. Which acid is stronger? Hydrogen sulfide, or what is that? Not sulfuric, but sulfurous. Hydrogen sulfite acid.
The one you couldn't pronounce, the second one.
The second one? I don't know. I got to find them. Here's H2SO3, right? And where's H2S? Oh, yeah. Right? So she's right. Does everybody agree? Because that's higher in the table? Okay. How about this last question here, Kenneth? Can any of the compounds in the table act like an acid or a base? Like what? What's something that could act like an acid or a base?
Water.
Water. So in other words, he sees water on both sides. Is it? You're right.
It's on there.
Well, I don't know if I can't find it.
Oh, yeah.
Oh, yeah. All right, so it has to be something that's on both sides. Is there anything else? HS negative.
From where you drew the arrow.
Yeah. So there's several compounds that can act like an acid or a base. Okay. So is it going to act like an acid or a base? Well, it depends on what else is in solution. So to answer Cameron's question about recognizing bases, it's not very straightforward at all. All right. The strongest conjugate acid has the weakest. Yeah, I just added that. Weakest conjugate base. Oh, the weakest conjugate acid has the strongest conjugate base. Yeah, I just added those. Not that big a deal. We've kind of hashed that over and over. Okay. So what we are going to do now is we're going to be given these reactions, and we need to predict them. So Andrea, it's like covering up this side, covering up the products, and you have to identify what the acid and the base are you're going to get. And then you have to draw an arrow and say which direction the equilibrium lies. In other words, are you going to have mostly reactants or mostly products? Okay, and that's the game that we're going to be playing. So let's see if you can answer this first one. Acid-base reactions are always of the form above. So acid and a base gives acid and a base. Reactants are always blanks of the products. Conjugates. These guys are always conjugate-base, acid-base pairs. That's how you're going to predict these. If these aren't there and you have to predict them, just do conjugates. Conjugate of this one. Conjugate of that one. Okay. And then the direction, right? Are you going to draw the arrows going, oh, it's this way? We have mostly reactants, or we have mostly products. You know, which one is right? It's the predominant direction. And this reaction is always bounty towards the blank acid. Which one are you going to have the most of? Because you're going to have an acid on both sides. You could do the same argument for the base, but it's just easier to pick one. So we're going to do acid. Are you going to have more of the stronger acid when you reach equilibrium, or are you going to have more of the weaker acid? You're going to have more of the weaker acid because the stronger one breaks apart. Exactly. That's exactly right. You're going to have more of the weaker one because the stronger one breaks apart. So the arrow always points towards the Weaker one. That's where you're going to have the most of. We like to always write arrows going like that. Well, now they're trying to say, well, nah, well, what if this guy's weaker? Well, then you have to draw the arrow like that, saying that, hey, you have mostly, even though these are reactants, you have mostly reactants at equilibrium. So that's what they're trying to show with that arrow. Okay. So predict the product's end direction of each reaction. We need a game plan for this, Cameron. So it's going to be this way, or it's going to be that way. And then we have to say what plus what. Make this space it out a little bit more. Okay. So we have to predict the products and the direction. What do you think? So over here we could, now remember these have to be conjugates, right? I guess what I'm shooting for is identifying what's what over here. Because remember, didn't we say, and we did, we circled it. Hydrogen sulfide can go either way. So, right? But can this one go either way? No. So this H2SO3 has to be a acid. This has to be an acid. So its conjugate has to be a base. So you have to write the conjugate base of H2SO3. That's how I figure these out. I look and see which reactant does not have a choice. And H2SO3 has to be an acid, so you have to write the conjugate of H2SO3, Mia, which is what? What's the H with a negative, right? Because you have to take away an H plus. Before it was neutral, so this is 0 up here. Subtract 1 from it, well, you have a negative 1. So you're taking away an H plus. So you have HSO3 minus. So this has to be acting like a conjugate acid. This has to be acting like a conjugate base. So that means we have to write the what, Kendall, of hydrogen sulfide? Yeah, this has to be acting like a base. This has to be acting like a base. If this is a conjugate acid, it has to be a conjugate base. Exactly right, Kendall. That has to be a conjugate base. So this has to be a conjugate acid. Or we can look at it this way. If this is a base, this guy has to be an acid. So you're right. The conjugate acid is going to be, everybody, H2S. All right, so see if you can figure out the next one, B. Oh, we didn't do the direction. We got to do the direction. Jose, what was the rule for doing the direction again? It points towards the weaker acid. Okay, so which one is it going to point towards reactants? I guess it's going to point towards H2SO3, or is it going to point towards H2S? H2S is weaker. Everybody agree? Yeah, so it has to point towards H2S because that's the weaker one. Okay. Has to point towards the weaker acid. So now do the same thing for B. Write out identify what the reactants are. What's acting like what. So you can predict the products and then predict the direction. So Audrey, what did you pick as your products? H2S and Cn the negative. Does everybody agree? Good deal. All right, because HCN has to be acting like an acid. So you had to draw its conjugate base on the other side. How about the arrow direction? Andromeda, towards reactants or towards products? So we're comparing H2S and HCN. Those are our acids.
HCN is weaker, so H2S. Oh, it's CN. I think those were resistance.
Right? HCN is acting like a conjugate acid. H2S is acting like a conjugate acid. So HCN or H2S, everybody, it's HCN is weaker? I don't know. I don't remember it. Well, I have both these arrows pointing the same direction. All right? So it should point towards the weaker one. Everybody agree? Good deal. Predicting acid strength from molecular structure. So usually you can just look at the table, right? And you say which acid's stronger or weaker. But there's going to be some homework questions where they're not going to be in the table because these weak acids are everywhere and there's a lot of them. So for acids, I changed this a little bit this morning, but it's pretty much the same thing you have in your notes. For acids, HX. And X is an element in the same group in the periodic table. So groups, Steph, are they columns or rows? Columns. Groups are columns. Okay. So as you go down a column, those elements get bigger or smaller, Megan? As you go down a column. As you go down a column, they get bigger. Okay. So this X is getting bigger and bigger and bigger as you go down the group. Then the blank, the bond will be. So in other words, you have this bond HX. As X gets bigger and bigger and bigger, the bond gets, what would you argue? Weaker, right? It's kind of like charge distribution. It's spread out farther and farther and farther. So the bond gets weaker and weaker and weaker. Well, then the acid gets, if the bond is weaker between H and X, it's going to fall off easier. So that acid's going to get stronger. So as you go down a group, dang, those acids are getting stronger. Okay. For acids, HX with elements X that are in the same period. So now we're going across the periodic table. The more polar the bond, this is a hard one, then I don't know if you got this out of the reading or not. You got a 33.3% chance of getting this right. Who feels lucky? Then the stronger. Ooh. Audrey, go buy a lottery ticket. The stronger the acid strength. The more oxygens that are present, then the... Now the only hint you have to this one is pretty much looking at what's the strongest acid in that whole table. Look at all those oxygens in HClO4. So the more oxygens, the stronger. Right? Look at that. Okay. Do you notice too? Look at this. HCl, look at HI is the strongest out of those three halogens because I is the biggest. That's why HI is stronger than HBr, which is stronger than HCl. Let's see. Use the table. So here's just some questions. We'll wrap up. See if we can knock these out. You might get out of here early if you can get through all this stuff. Did you want to go to the boards? People. All right. Use table 15.2. That's that table of all the strengths. Decide whether the species on the left or those on the right are favored by the reaction. So that's the same idea as drawing that arrow, right, towards reactants or products. So you need...
Both ways, you have to
Yeah, you have to determine which side is going to be dominant at equilibrium. Will you have more reactants or will you have more products? So you need to identify what's acting like a acid on both sides and compare them, compare their strengths. Which way, yeah, so there's a lot of different ways of answering that question. Which way will it be favored? That's the same as saying, which direction is the arrow going? That's the same as saying, which one will you have more of at equilibrium, reactants or products? Which one will dominate at equilibrium, reactants or products? What's the dominant form at equilibrium, reactants or products? Those are all the same way of asking the same question. So what two acids are you comparing in C? Just to make sure everyone's on the same page here. HCO3 minus and H2O. Can this act like an acid? Can hydroxide act like an acid? No, that's almost our definition of a base, right? So no. So you have to compare these two. Those are our two acids. Even though HCO3 minus can go either way, here it's acting like an acid. It's giving up an H because carbonate is its conjugate base. There's a lot of ways to look at that. So which one's weaker? HCO3 minus is? So I guess you'd say reactants. Water's weaker? Yeah, water's way in the bottom, isn't it? All right, water, let's just check here. Our acid strength, yeah, the very bottom is water. HCO3 minus is right here. That's pretty weak too, but not as weak as water. So see if you can answer all of these. Shouldn't take too long. Then we'll see if we can come to a consensus. So what'd you say for D? I mean for this guy. Going towards products again? Let's see, so we're comparing. All right. How about for 48? 48B. What did you say, Kenneth? Reactants or products? What's gonna, or first tell me what the two acids are. H2S and H2CO3. So which one's weaker? H2S. How about C? What are the two acids there Andrea, what are the two acids in C? H2O and HCN. The weaker one is? Yeah, H2O. How about D? Bowdy, how about D? The two acids are HCO3 and HCN, and the weaker one is HCO3. Okay, good. We're almost done. For each of the following pairs, circle the stronger one. And you're supposed to explain. Okay. Mia, what would you say for the first one? Which one's stronger? I'd say, yeah, but why? More hydrogens, I would say that too. That's a good answer. Has more hydrogens. First one's going to be a lot easier to give up than the other one. Kendall, how about B? H2SeO3. Why that one? Yes. Yes, Se is bigger. In the same group or period? Group, because it's up and down. One left. Jose? Yeah, you guessed right. Why? More oxygens. Perfect. So have a good weekend.